I'm Matthias Degroote. I'm part of the quantum computing lab at Boehringer Ingelheim. We're a large pharmaceutical company out of Germany, and I'm going to tell you now, basing myself on two use cases. I'm going to tell you about the research progress that we've made, and trying to convey the message that there is progress, that things are moving forward, and even if it feels like fault-tolerant algorithms and applications are very far off, things are going forward, and resource requirements are coming down, and it does look like applications are closer than you might think. So the first thing that I'll talk about is ground state calculations. So when our team was established in 2020, there were not so many systems that one would calculate on a quantum computer around. There's the classical FEMOCO nitrogenase system that is involved in fertilizer, but that's not really of interest to a pharmaceutical company like Boehringer Ingelheim. So in a collaboration with Google and our computational chemistry team, we were tasked to find our sort of pet molecule that if anything fails and we can only do strongly correlated molecules on a quantum computer, that we would have one out there that we are interested in. And so we settled on P450. It's a molecule in the family of cytochromes, a sort of protein in the body. And it's very important for the breakdown of drug molecules in your liver. So when a drug enters your body, you hope that it's not around forever and that eventually it exits your body, and this molecule, P450, helps breaking down the molecule in your liver. So the system size is 58 orbitals. We spend a lot of time finding consistent active spaces, growing the system from a very tiny toy system to something where you would gather some information. And as you can see in the plot here, on the top right corner, eventually the green line, which we estimated resources for on a fault-tolerant quantum computer, crosses over with classical computers. We did the full treatment of this, and we came out that eventually we need 1,400 logical qubits. And if you know the numbers that are around right now, that's very far out, and 7.8 billion gates. And these gates you would execute on about 4 million physical qubits, and that would take 3 days. And when you get those numbers, you're happy that you know it, but that also is not very realistic. Like if you work in a pharmacy company, people really need real-time answers. So our scientists would tell us that they can synthesize this molecule in less time than we could calculate it at a very much lower cost. So this was a sign for us that something needed to be done. And this was the start of a very fruitful collaboration with QCware, where we had 3 projects that really dove into the particular things that needed to be improved to get a speed up on quantum simulation. And the first one is a paper in PRL by Pauline that basically improves the overlap with the initial state. At the time, there was a lot of controversy that we could not create initial states for these kind of systems, and we basically showed that there is a problem, but you can do much better than we thought at that time. The second project was about figuring out how much improvement can you expect. So you get this number, it's 3 days, but it's not going to go down like to microseconds, right? So what can you expect? And in that second paper, we developed sort of quantum speed limits, and we recognized that current methods were bound by the highest speed limit, and that you could do better by being smart about the compression of the Hamiltonians. And of course, when you find such good signal, you dig deeper, and that's the third paper where we, for the first time, sort of violated the first speed limit and went blasted past it and found a much better compression algorithm for the Hamiltonians. So just to show you that if you get sort of a disappointment, you can find the reason why and then start tackling all of the elements and improve them. All of these 3 projects, they gave us sort of a part of the whole picture, but of course you have to tie it together again, and that is really a very large task. And so we teamed up with PsiQuantum to do this and to sort of take all of the learnings and integrate them again in a specific resource estimation. And we expanded past the compression on the previous slide, and we now beat 2 out of the 3 speed limits. And we think that the third one is very hard to achieve. And I think by now we are a factor of only 2 above the theoretical speed limit that we don't think you can pass. So if you think pharmaceutical applications will go much faster by now, or you project that in sort of your pitch decks, you need to be very careful, because we are sort of approaching what we can achieve if we do not change the algorithm, of course. And there was another reason why we partner up with PsiQuantum. They had developed a new type of architecture, which is called the active volume architecture. And so they now count resources in a different way, which is taking into account how their machine will execute calculations. And that means that now we can compare the resources that you need, and it's sort of focused on just 2 numbers. So this one here, this 42, 10 to the 12, and then this one, which is a factor of 200 lower. So basically, by doing a better compression and leveraging the architecture that PsiQuantum is developing, we are able to decrease the logical resources by a factor of 200. So this is now the logical thing, and then again, you have the hardware-specific compilation into physical resources, and that's on the side here. And here you can see that we go from an estimate that was about 3 days, or 3 hours in this case, and you can go all the way down to 10 seconds. You must take into account, it's not just on any device, right? The first device they will make will not have 400,000 interleaving modules. The first device will be around this footprint, they told us. And so you can see it's already an improvement from 3 days to 3 hours. But even taking into account real hardware, you can achieve very large speedups. So there were a few learnings from this sort of research project. And one is the snowball effect. Like you start doing something, and immediately when you publish a paper about a molecule, new questions show up. You learn something, but every new answer brings up 3 more questions, and it really naturally provides you with a research program. Like the second slide I showed really came out of the first project, where we were really frustrated that we could not perform this calculation as fast as we would want it. And the second one is that by asking ourselves the question, what would we calculate? We established a benchmark. So we have this system, this P450, and if any technology or any progress shows up, we can ask, can you apply this to our P450? And we can compare the outcomes. It's not only that you can challenge progress by it, but you can also measure progress. So if it doesn't work for this molecule, or you do not improve things compared to previous results, you know that it's not as good as it should be. And then, of course, number 3 is like a bit of the pessimistic statement. If everything else fails, we know that we can do this. If we calculate this molecule, we do get data that we care about. And I think many industries are still looking for this sort of first signal of something you can definitely do if the machines get large enough. So one of the criticisms that you get when you say that is, of course, that this molecule is not the most important molecule in the world to a pharma company. Many of our drugs are not strongly correlated, and so this is only a very tiny slice of what we do. And of course, you can always like count the impact by how many times you would use it times whatever you improve. So we were looking then at something that we use many times in almost any project that shows up in our computational chemistry. We use molecular dynamics. And molecular dynamics is basically the way you look at a molecule over time. So you follow its atoms while they move under each other's influence. And it's used in many applications. For instance, free energy calculations that is trying to find sort of the binding energy of a molecule to a protein pocket. It's a molecular microscope, so you can follow reactions and see them happen over time. And yeah, it's also the driver of the way how we find equilibrium geometries. It's sort of the same principle. You calculate forces and you move the atoms until they are in their most favorable position. So yeah, we know how to do this. Classically, we do this by taking derivatives of energies. So we thought in a project with Google and the University of Toronto, let's copy the classical workflow and let's do this also on a quantum computer. And we put out a paper in Physical Reviews Research where we did that, and we did that both in NISC and in fault tolerance, and we found that that you can do it and that it's not that costly, but not cheap enough to do it in a framework where you need many repetitions. Because when you do these calculations, you have to have a very tiny time step between different calls of your molecular forces. So this is not a single point calculation. This is something you repeat millions of times. And if you saw our resource estimates for a ground state calculation, we got the force calculation to about the same cost, but that means that 1 million times 3 days, you don't have that time. We also did a project with PsiQuantum where we took all of the best machinery doing quantum singular value transformation and block encodings to really narrow this down and to find constant factor resource estimates. And it's something that nobody had done before. And again, it's sort of a eye-opener, right? You think you can do something. You think you can do molecular dynamics. It's quoted as an application that people want to use quantum computers for. But when you do the math and you like take it one step further and ask how would you do it and what would you need to do it, it's sort of sort of a disconcerting answer that you get. And of course, needing to rethink something, it means that you do not just copy the solution that was around. And we actually developed an algorithm together with our colleagues from the University of Toronto. And what we did is we tried to not extract the forces from the quantum computer. Instead of copying the classical workflow, we now encoded everything in a quantum wave function, also the positions of the nuclei. This requires quite a lot of tinkering and development because this is not a unitary transformation. So if you know quantum computers, they can do only unitary operations. So it takes quite a lot of effort to actually make this work, but we did it. And then I think just last month we brought a paper on the archive which does it better, with same authors from the University of Toronto, but now joined by Oxford and Quantum Motion, where we bring down some of the costs that are involved. So we could actually do the Liouvillean evolution before at a polynomial cost, but what we couldn't do was extract the binding free energy without an exponential cost, and that's sort of something that we overcame in this second project. These are very technical papers, so if you care about a more like gentle intro into this, please talk to me. But yeah, the gist of it is that we can now do this application, which is calculate free energies at a polynomial cost with a very large quantum algorithm. So again, when you do these things, it's you learn a thing or two, and for this one specifically is that all of these applications, you need to tailor your quantum algorithm. You just cannot blindly do for relative free energies the same as you do for absolute free energies. You really need to fit your algorithm to what your application is. Between the two projects on the free energy, there was a lot of differences as well. So there goes a lot of tuning into finding a fault-tolerant solution that is actually also faster. And then, of course, the second one, I think many people have noticed that if you just copy classical workflows into quantum, it gets kind of tricky. And it's not obvious that you would find a speed up there. And then the last one, sometimes if things don't work, you need to scratch what you have, right? Like start all over, and then yeah, when we found that the forces did not work, we had to find different partners, look for new ideas, and really try it from like zero, like square one. And what you do have is the gained experience. You know a lot of things that don't work, you know why they don't work, and that helps speed up the development eventually. So with that, those were the two use cases that we have sort of a research arc on, and yeah, that we think that we are driving in a successful direction. And I would say for like the business side of things, I think that these three conclusions are very valuable. I think if you do research like this, knowledge keeps on building. So if you find an outcome, you get a better view of why you are in quantum, what it will bring to you, what will be the benefit, what will not be the benefit. So they give us so many data points, these projects, where we want to be in the space and why, and what will be the benefit to our company. And it's sort of a good motivator also for executives to know why you are doing this and what are the signals that we get out of our research. And then, of course, we try to publish everything we do, and that means that your publications get noticed, people contact you, you have a very strong influence of what happens in this space. And I must say that before we started this research track, I couldn't point to a lot of papers that had this pharma angle and that were really solving problems that we had. Things were very academic and sort of very out of tune with our real demands. And then the last one is sort of a call to action. I think there's still way too few algorithms that are really going to deliver value, and in the same vein, way too few molecules. Like, I think if you are in an industry that does quantum simulation for molecules, putting forward like this North Star, this thing that you can definitely calculate, people need it. Like, I think the hardware people want more of these. I think it serves your industry well to do this, because then you can convince people that, yeah, that value will be created if you do this. So, yeah, thank you, and please reach out if you have any questions.